So hello, welcome to week 2 of physics. Today we're going to start chapter 2, which makes sense. Week 2, chapter 2. We're not going anything crazy here. And we're going to actually start actual physics this chapter, because since last one wasn't really much of anything. And what we're actually going to talk about is motion in one dimension. Basically, we're going to be just moving in straight lines back and forth, side to side or up and down. 2 dimensions will be next chapter. But yeah, we're going to get into motion. So before we can talk about motion, we just have to define a few terms in general before we can deal with things moving. And really one term we have to define before we get into motion. And so I'm going to start with talking about position. Position, which I'm sure you're aware of this fact, is the location of something. But the thing is, to define the position of an object, you have to have two different things. Anytime you want to define the position of an object, you must have a 0 point. Think of the idea if you're measuring the length of something, right? I got my tape measure. If I'm measuring the length of something, I'm just saying what the position of the far end is at. But I have to put the end of the measure somewhere. Like I need to put this up against something or else I won't be able to kind of work anything out. And the same is true with position. That if you say something is at 20 meters, it's not really that meaningful to us. We have to say it's 20 meters from another object. Though whenever we define the position of something, it is always relative to another thing. And so when you're defining the position of any object, you must have a 0 point, aka where you are measuring from. You also have to have a direction. So if I tell you the distance between, if I tell you how to get from Oneonta to Delhi as you go 20 miles, it might get you in Oneonta, but you might instead go straight south. I didn't necessarily say what direction. And going 20 miles south of Delhi is very different than going 20 miles northeast. East? I think it's actually northwest. I need to look at a map. It's a very different idea. You need to know what direction to travel in. And so that's the other thing, is anytime you want to say about position, you have to say where, not only where you're measuring from, but in what direction. Now, when we define the position, in physics, I'm going to use symbols for everything. And position actually has 3 different symbols, X, Y, and Z. X will be, by definition, anything along the x-axis, aka for the most part normally horizontal. And so if it's moving right or left, we'll normally define its position in x. Y will be given on the y-axis, up and down. And Z, our third axis, is going to be kind of into and out of the page. We're never going to use Z in this class, really. We're going to talk about things in the Z axis, but it's not really going to come up much. For now, we just got to deal with X and Y. Well, X will be horizontal and Y will be vertical. And so, yeah, if you see me say something in position in X or position in Y, I just mean position. We will be working, position will be measured in meters, although you might sometimes see centimeters or maybe feet or kilometers or miles or something else, but we need to work in meters. There we go. This says I did something different, but I see nothing different. I have to fix that. Now, what we want to talk about, though, is motion. And so position is kind of boring. I'm just like, hey, look, this thing is here. Woo! No one gives a shit. If we're going to talk about motion, we got to talk about things are moving. And so we are going to often talk about displacement. Displacement is, by definition, your final position minus your initial position. This equal sign with a third line on it, that just means by definition. And so displacement, which usually symbols delta x, which just stands for change in x, so it kind of is the same thing, is just how something changed its position. You might also see delta y for y final minus y initial, or delta z for z final minus z initial. But displacement is just how the position changed. Where did it start? Where did it end up? Here's the important thing, though. Displacement is just final minus initial. And it doesn't get counteract of how you get from point A to point B. It's where did you end? Where did you start? Where did you come from? Where did you go? Take, for example, this ship here. If the ship is at a position x1 and moves across to x2, I would say the displacement is just final minus initial, x2 minus x1. Pretty straightforward. But let's say this ship instead did this and whizzed all around the screen, did some crazy ass path that just go wee, whoop, and ended right there. If it does that, its displacement is exactly the same, because displacement doesn't care how you get from point A to point B. It's just where did you start, where did you end. And so even if it goes and does this path to get there, that's still the same displacement as when it just did this, because we don't care how you travel. Likewise, if this ship was to start here and make a big circle and start where it ended up, its displacement is 0. Its displacement is 0 because it started and ended at the same spot. It might have moved, but it doesn't matter. Displacement is just where is your initial, where is your final. When something is moving, displacement isn't distance, and are very often different. If I take a ball, and I'm going to try to make everything fit. If I take a ball and throw it straight up, right now, this ball is right here. When I throw it, take a look. It's pretty close to the exact same spot. It's not exact. I'm doing my best here. But it started and stopped in the same spot. That means when we go from here to there, its displacement was 0. But the distance it traveled is that it started here, went up, came back, and went down. The distance it traveled was twice its height because it went up, then down. And so distance and displacement are not the same. Displacement is just where you ended up minus where you started. Distance is the actual path you traveled. We good?
So, Professor, I'm a little confused because when I picture the formula for distance, it basically looks like the same equation but with a square root sign.
I'm not sure which formula you mean.
Oh.
Are you talking, there's no set equation for distance. If you're thinking like last chapter, the Pythagorean theorem one, the square root of x squared plus y squared.
Yeah.
Because that is a radius that we're going to use for a distance if we're going straight there, but it's not quite the same by a distance here. For distance here, I mean if something's moving from point A to point B, what path it takes.
Okay.
Does that make sense?
Yeah.
Okay. Now, let's say we look at the position as a function of time, something moving. And this is stolen from a textbook, but what that's supposed to be showing right there is, not that. My videos didn't merge together correctly today. This one. I put it on a slight ramp just so I could match it. But what I have is a car that's starting at some point 30 meters above the 0. That goes up and then comes back down below. That is what this is showing. It starts at A, goes up to B, and then makes it all the way to F afterwards. Right? Boop, boop. So that matches this picture. Now in this, they measure their 0 point. They define their 0 point as right in the middle. And so I can say, if I look, I can talk about its position. Oh, nope, that can't be its 0 point because that's where it started. Let's make this my 0 point. It's not quite the scale the same as the picture, but that way it's starting above it. So it's starting with a position somewhere in the positive direction to the right of the 0 point. It goes up and it comes back down, ends up to the left of the 0 point. I can use this to plot the distance, the position as a function of time. And if I plot the position as the function of time, I'll see it went further in the positive and then back down towards negative. Note, to measure the position, once again, I have to define a reference point. And I have to decide which way is positive. I said at the beginning. But if I look at this, I would say it started with a positive value, went up to a bigger positive value, went from 30 to almost 60, and then went back down past the 0 in the opposite direction. It went from positive to negative. If I were talking about displacement, I would say displacement would just be my final position, right here, minus my initial position, right there. But I would say my displacement was that net, it went in the negative direction. That it started here, it ended there. And what it did in between, the fact that it went up, then down, doesn't matter. Its displacement is just it went here to there. And what happened in between is completely unimportant to displacement. Okay? Now of note, I did say its displacement was in the negative direction. This gets the idea of vectors and scalars. Displacement and position is what is called a vector. A vector is a quantity that has both a magnitude and direction. That it has not only how far something it moved, but in what direction. In that little bit I was just showing, it ended up going to the left. I would say that's in the, if I define a standard axis, if it went to the left, I would say it went in the negative direction. Because the standard axis, I'm saying to the right is positive. If it's going to the left, it's in the opposite direction. Any vector, you must include not only the magnitude, but the direction. Now, for the most part, when we deal with one-dimensional, things are either going to be straight along x or right opposing x, or straight along y or right opposing y. And so traditionally, we'll just say things are positive or negative. That anything pointing to the right, I'll just say is in the positive x. Anything pointing to the left, I'll say is in the negative x. Pointing up, positive y. Pointing down, negative y. Now, this is true for all vectors. Once again, position and displacement being vectors. Some numbers don't have direction. Take, for example, mass. I could say something has a mass of 180 kilograms. It's not 180 kilograms going to the right. It's not 180 kilograms going to the left. It's just 180 kilograms. Time is like that. You don't travel, if you say something like you're going to wait an hour, you don't wait an hour when moving to the north direction. It's just an hour. That is a scalar. A scalar is anything that has only magnitude and are almost always positive numbers. There's some exceptions to that we'll talk about much later in the class. But in general, the terms I've introduced so far, position and displacement, those are vectors. You need to say not how far something moved, but what direction. Or not where something is, but in what direction. Now, if you're using a standard coordinate system, once again, this guy, we can just define positive and negative as we could just define the direction as positive or negative because we're only doing one dimensional. We're not doing anything arcing. We're just doing it going like this or going like this. And so we can just say for one dimensional, we'll just say it's positive or negative. That will represent the direction. Okay. Example on this. This example makes a lot less sense online because in person, you would learn this if you ever saw me in person. I don't stop pacing while teaching. Here, I just sit in a chair, which means very great for me, I guess. But let's say during class, I start pacing around. And I start 7 meters to the, I start at one spot. And I move 7 meters to the right. I then move 12 meters to the left. I then move 9 meters to the right again. If I take right as the positive direction, what's my displacement? You see, this will work as long as I deal with the fact that everything is vectors. My displacement is just my final position minus my initial. And if I define an axis and define a 0 point and a direction, I said to the right was positive, I can say what it all is. Now, what I'm going to do is I'm going to define wherever I started as my 0. Since displacement is x final minus x initial, I'm just going to say x initial is 0. And this is a trick in physics. You define where the 0 point is. And if you define where the 0 point is, if you want to measure displacement, make your initial the 0 point. Same as if you're measuring something. If I want to measure the length of this thing, I'm going to put the end of the ruler at the end of the thing. I could measure the distance by putting the end of the ruler here and then measuring how far to the left it went, but that's just a pain in the ass. I'll say my initial is my 0 point and say I initially moved 7 meters to the right. The right was the positive direction, so that's a positive 7. I then moved 12 meters to the left. The left is the negative direction. So that displacement isn't 12 meters, it's negative 12 meters because it's to the left. I then moved 9 meters to the right. Right is positive, plus 9. My total displacement is 7 minus 12 plus 9 meters, or 4 meters. Questions? So I just play with my z-axis. That's a weird sentence. Okay. Now, just saying something's moving, that's kind of boring. Where this gets interesting, we start talking about how fast something is moving. And you're probably familiar with the idea of speed. Speed, you know, is just how fast the thing is moving. Speed, or at least average speed. Because if I go back to this coat right here, it's changing speed as it goes. It's speeding up, or it's slowing down on the way up and speeding up on the way down. Average speed is your speed on average over a trip. And average speed is defined as the total distance over the total time. If I wanted to find the average speed of this motion, I would just say, okay, it started right here. Its distance traveled would be this, this, this. And I would find that total distance. And the speed would just be that total distance over the total time, or at least the average speed. Now, speed is a scalar quantity. It should always be positive. Average speed, though, it ignores all variance in the motion. That coat I just showed, it slowed down then sped up. It doesn't give a shit. Average speed is total distance over total time. Also, since speed is distance over time, its units will be meters per second. But here's the thing. Speed is pointless, useless, and we're never going to use it. Because speed just... the distance something travels isn't necessarily that useful. Then on my coat guy, I can say, okay, it went up then down, find that distance. But we already said we want to work with displacement. The displacement says it started here, it ended there, and is ignoring what happened in between. That by working with displacement, we can simplify the problem and make the math work. And so we're not going to talk about speed. Speed might be distance over time, but we like to deal with displacement. And instead, I'm going to use the term velocity, where speed is total distance over total time, or average speed is total distance over total time. Average velocity is total displacement over total time. That average velocity is just going to be where it started, where it ended up. And if I go back to me throwing that ball up, which I think was on this one, not throw down, throw up. When I throw this ball up, I would say its average velocity is actually 0. Its average velocity is 0 because it started and stopped at the same spot. It seems like I'd get less information out of this, but I actually get a lot more because it accounts for also direction. See, velocity, which I didn't say this out loud, velocity uses the symbol V. Anytime you see a V, that's velocity. VAV, as I wrote there, is average velocity. We're not going to talk about average velocity much. We're mostly going to talk about instantaneous velocity. I'll explain why in a second. But V is velocity, also measured in meters per second. It is the rate at which displacement occurs. So yeah, we're just going to say that the average velocity is just the displacement over time. Okay. Now, as I already said, velocity is a vector, which means the direction of your velocity is the direction of your displacement. I will sometimes ask for the magnitude of velocity. If I ever ask for magnitude of velocity, drop the negative sign. I just want to know what direction it's in. But I hate having to do these videos and not just being in person, because in person, I have all these things in the front of the classroom. What that means is that when the car on the way up, its average velocity is positive because it's moving to the right. When the car's on the way down, its average velocity is negative because it's moving to the left. That's how we're going to, that's why it matters these directions. Because now with velocity, we also say what direction it's going. Because if you're traveling 20 meters per second, it kind of matters which way you're going. And that's why when I throw the ball up and throw it back down and catch it, that's why the average velocity was 0. It's because on the way up, the velocity is positive. On the way down, it's negative. Average, it becomes 0. And so that's velocity. Average velocity is displacement over time. It is a vector. Always keep track of what direction it is. So once again, one-dimensional, we can just say positive or negative. To the right is positive, up is positive. To the left is negative, down is negative. That is arbitrary. You can change those, but that's the standard. Now to drive that message home, let's say I got 2 cars. One is blue, one is a weird orange color. It's actually the exact same. Now that I think of it, I took this, but that's the exact same color of my wife's car and my car, respectively. Anyways, and they move from point P to point Q, from X initial to X final. And let's say both cars do it in the exact same amount of time. That they get from P to Q, same time. Both cars will have the same average velocity because both cars have the same displacement. However, the blue car will have a larger speed than the orange car because the blue car traveled further. But the thing is that it doesn't account for direction. Its speed ignores direction. So yeah, the average speed is more, but it doesn't account for where it's going, which we need to account for while we're using velocity. But it also simplifies things. That P to Q, doesn't matter how I get there, this is what my average velocity is if I know the time, displacement over time. Thing is, and I'm kind of being bad with saying it, but this is average speed, average velocity. This is just on average. And if you're driving down the highway, you don't care how fast you went on average. What you're going to care about will how fast you're traveling the exact moment you pass that cop running radar. That's the important thing. Because you might have gone slower, got stuck in traffic, then sped up, but all that matters is the exact second that cop sees you, how fast were you going right then? And so instead of average speed and average velocity, we should talk about instantaneous speed and instantaneous velocity. And instantaneous speed is going to be the same in magnitude as instantaneous velocity. If you know what your instantaneous velocity is, you know your instantaneous speed. It's just you drop off the direction. Because speed is always a magnitude, velocity is always a vector. What it is, and I think I say this later on, and I don't know why this slide isn't here. You know what? I'm going to change the order of my slides real fast because I can do that. What it is instantaneous velocity or instantaneous speed is the limit of your average velocity as the time interval becomes 0. It's basically looking at your displacement over time for a very, 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 very small time period. I'm going to fix one other thing while I'm doing this. That is what it's going to be. Really, there's a derivative here. That's how you should be doing it. But this is not a calc-based class. Don't worry about the derivative. Honestly, I'm never going to have you do the limit. But basically, if we say that average velocity is just the total displacement over time, it's just the total displacement over time for tiny bit of time. That's how we get instantaneous velocity. Okay. Now, if you want to find velocity and you got hands on some graphing, we can actually find velocity if you look at position as a function of time. If you have a graph of position as a function of time, your average velocity will be the slope of the line joining the initial and final part. If an object is moving at constant velocity, like this, You can go over here. Okay. This car right here is moving at constant velocity. If something is moving at constant velocity, or in fact, I have a better one somewhere. I think this one? Nope. Flat. Aha! When I push this thing, it has velocity. When it hits the end, it has velocity. But while it's moving in between, it's moving at constant velocity. If I take this guy and I make a graph and show position as a function of time, it'll look like this. And that right there is just position as a function of time. I am still defining this pole that sticks up as my 0 point. And I'm saying it starts to the left of it, so it starts negative. It eventually moves to 0, and then moves past it. If it's moving at constant velocity, since average velocity is displacement over time, the slope of this graph, that will be my average velocity. Then if I go and just pick any 2 points, like B and A, I can say my average velocity will be my position at B minus my position at A, divided by my time at B minus my time at A. That'll give me my velocity. And if it's constant velocity, if it's not changing, I can do any 2 points. I can do B and A, I can do C and B. But that only works if the velocity is constant. If your velocity is changing, like it was on this guy is slowing down on the way up and speeding up on the way down. If your velocity is changing, and this is a graph of this motion right here, what's going to happen is that you can't easily get a slope of the entire line because the slope of the line is changing. Your average velocity, though, will be the slope of any, over a time period, would be the slope between any 2 points. If I want to find the average velocity between A and B, I would just make a straight line from A to B and find the slope. If I want to find the average velocity between A and C, I make a straight line between A and C and find the slope. If I want to find the average velocity between A and D, I do the same thing to A and D, and so on. Then I can say the average velocity is, if I were the average between A and B, it'd be position at B minus position at A, time of B minus time of A. If I want the average velocity between A and D, position at D minus position at A, time at D minus time at A, and so on. Now this kind of shows my instantaneous velocity idea, because what I'm saying is for instantaneous velocity, I'm just going to make this region of line smaller and smaller and smaller. And instead of saying, from A to D, or A to C, or A to B, I'm going to do A in something infinitesimally close. And that's how I'm getting my instantaneous velocity, by just making this time region small. So I forgot, I removed the slide that was next before because I just moved it. So I was expecting something else though. Any questions on this? Okay, let's see how well you guys are paying attention. I am going to try to make a poll pop up. I'm not always great at having this work, but we're going to try. So here's a question for you. Should pop up as a poll if I press the right button. One-dimensional motion, the average speed of an object that moves from one place to another, then back to the original place, has which of the following properties? 1 is positive, 2 is negative, 3 is 0, or 4 can be anything. So average speed of something that, I'll just do it with a ball. Average speed of this, that if it leaves my hand and I catch it at the exact same height. What is true for the average speed of that? I will give a minute.
Can I get my number back? I messed up.
Don't worry, it's not like I'm grading it or anything, so.
All right, I just feel dumb.
Sorry. Okay, pretty split. 40% said 1, 40% said 3, and 20% said 4. The answer is 1. Speed is a scalar. It is always positive. And speed, mistake. And speed is distance over time. Speed doesn't care how you get from point A to point B. It's just, well, speed cares how you get from point A to B. It's the total distance. Now that same thing, let's talk about the average velocity. If I throw it up and throw it down and catch it, what is the average velocity over that time period? That if I throw this, it leaves my hand, it hits the hand at the exact same height, what's the average velocity? People seem to realize. Okay, so 3/4 of you got it. That if it starts and stops at the same height, it starts and stops at the same place, that means its displacement is 0. If its displacement is, if its displacement is 0, that means that it's going, why can't I erase that dot? That means that it's going to have no velocity, because if displacement is 0, then it starts and comes back to the same place. Now, okay, that's velocity. But let's talk about what happens with the velocities changing. When I throw this up and down, what's happening is I'm giving it some velocity when it leaves my hand. It has velocity. It's going to go up, and it has positive velocity because it's going up. You know what? Instead of going back and forth like this, let's just go back to... Shit. Am I still in? Yeah, I'm still going. Sorry, Zoom just popped up with an alert to me, but I don't think it was anything. Okay, whatever. This says I'm still in here, so I assume I am. Okay. When I throw this up and to catch it, what's happening is initially it's traveling upwards, right? So it has a positive velocity. On the way down, it's traveling downwards. It has a negative velocity. So its velocity is changing. So let's get into what a change in velocity means. See, velocity, displacement over time in meters per second. If we start changing velocity, we can talk about acceleration. Acceleration, which uses symbol A, or average acceleration, which uses symbol A, is change in velocity over change in time. An average acceleration would just be how much the velocity changed in a time period. Now, unit-wise, velocity is meters per second, and we're taking meters per second and dividing by time. So units of acceleration would be meters per second squared. And we can say for any time something is changing velocity, we can talk about its acceleration. In this version for velocity I kept using, I have these lights on top. These lights are an accelerometer. They're showing the acceleration. What you can see is when I push this thing, I give it acceleration. That's because I'm increasing its velocity. It's going up. And then once it starts moving, it has an acceleration downwards. A nice constant acceleration downwards until it hits the bottom. Because at all points it's accelerating that way. As opposed to when it was flat, when I pushed it, it had acceleration, but then it had basically no acceleration as it moved because it wasn't accelerating. The velocity wasn't changing. That's what acceleration is. Change in velocity over change in time. Now, if your velocity is constant, your acceleration is 0. You can be moving. That's this again. From here. But if your velocity isn't changing, your acceleration is 0. This is showing a little bit of red blinks as it goes. That's because there's a little bit of friction. It's slowing down a tiny bit, but it's pretty negligible. However, if your velocity is changing, you'd like to think acceleration means speeding up. And so a lot of people, but acceleration just means change in velocity. If you're slowing down, that's acceleration. And a lot of people like to think positive acceleration go faster, negative acceleration goes slower, but that's not true either. See, if I look at this, this idea, in knowing when I'm pushing on it, on the way up, it's slowing down when the acceleration is down. But on the way down, it's speeding up when the acceleration is down. The general idea, if acceleration and velocity are both in the same direction, if acceleration is this way, that doesn't show up well against me. If acceleration is this way and velocity is also this way, you're going to speed up. That if they're both the same, you go faster. If they're both positive, you go faster. If they're both negative, you go faster in the negative direction. But when they're in opposite directions, that's slowing down. If your velocity is positive, your acceleration is negative, you're slowing down in the positive direction. If your velocity is negative and your acceleration is positive, you're slowing down in the negative direction. I think I said those correct. And so this guy on the way up is going slower because its velocity is to the right, its acceleration is to the left. And on the way down, it's speeding up because its velocity is to the left and the acceleration is to the left. The acceleration didn't change during this, except when I'm pushing on it. But the entire time I'm not pushing on it, the acceleration is constant. But it can switch from going faster to going slower depending on the direction of the velocity. Okay? Okay. So before I get further, because, obviously I'm going further, I have to introduce a notation. Everything so far I've been doing final minus initial. That is not standard notation in physics. Some of you who took physics in high school might have seen equations with T final, T initial, X final minus X initial, but once again, it is not the standard notation. It's something sometimes people use to make it easier, but that's not what we're doing here. We're trying to do it right. See, most of the time in a problem, you don't have initial time and final time. You have how long something took. If you're going to time how long something is, you don't just keep the clock running. You start the stopwatch when it begins. And so what happens is almost always when we're looking at something, we're going to say our initial time equals 0. Because our initial time is when we're going to start timing something. And so T initial is just always going to be 0. And so since T initial is always 0, instead of TF and TI, we'll just use 0 and T, where T will just be time at some point. And T equals 0, we just use 0 because 0 is 0, 0, 0, 0. This introduced the sub-not notation. Well, for every term, position, velocity, acceleration, we'll put it in 2 categories. The one that happens when T equals 0 and the one that happens when T doesn't equal 0. And anything that's when T equals 0, we'll give it a subscript 0 or a sub-not. So my velocity when T equals 0 is V sub naught. My position when T equals 0 is X sub naught. And my time when T equals 0 is 0. And so what it's going to be is instead of initial and final, we're going to have sub naught and just regular. That X sub naught is initial position. X is final position. V sub naught is initial velocity. V is final velocity. And that's how we do these notations. Now that we've seen that, we can introduce what is called kinematics, which is going to be the majority of this chapter. Although I know I'm mostly done with today, but majority of at least Wednesday. And here's the thing. We're going to make an assumption. We're going to assume acceleration is going to be constant. See, so far we've only said average acceleration. We're going to say, screw that noise, acceleration is constant. If your acceleration is changing acceleration over change in time is a joke, like if you joke to a stop. We're never going to talk about that. Let's assume acceleration is constant. And we're going to say if acceleration is constant, our initial conditions, T is 0, V is V naught, position is X naught. This could also be Y naught or Z naught if I had X or Y. And we're going to say at some time later T, your velocity is V, your position is X. And what I'm going to do is a shit ton of algebra. See, I already said average acceleration is V final minus V initial over T final minus T initial. So that means average acceleration in this notation is v minus v naught divided by t minus t naught, but t naught is 0. So it's just v minus v naught over t. But if your acceleration is constant, your instantaneous acceleration is the same as your average acceleration. So that means acceleration is v minus v naught over t. If I take that equation and I multiply both sides by t, I get that at equals v minus v naught. If I then add v naught to both sides, I get v equals v naught plus at. What this says is your velocity as a function of time, that if something is accelerating or not, its velocity as a function of time is going to be its initial velocity plus acceleration times time. This will give you velocity as a function of time. That's the only thing you need here. In fact, of all the equations I introduced so far this chapter, this is the first one that actually matters. Okay. Now, let's go for another equation. I also said that V average is change of position over change of time. V average is displacement over time. But here's the thing. I just introduced, if I rearrange that, I can get this equation right here. I'm not showing me rearranging it because it's the exact same logic. I multiplied by t, added x naught. So let's take that equation. Position x equals x naught plus v average t. V average no one cares about. We want to use instantaneous values. But average, if you want, okay, let's say you want to take the average of two numbers. What do? You add them together, you divide by 2. Logically, your average velocity should be your initial velocity plus your final velocity divided by 2. And if I say my average velocity is just I take the average of two numbers and I plug that in for V average, I'm going to get this equation. But I just said last slide, or 2 slides ago, that V equals V naught plus AT. So I'm going to take this V and plug it in right there. And that gives me this. Now I got a V naught plus a V naught, so I'm going to add my 2 V naughts together. And I'll factor out the 2. And this is your second important equation. See, the first equation I circled is velocity as a function of time. But the second one gives you position as a function of time. If you want to know the position of an object, the position of an object would be its initial position plus its initial velocity times time plus 1/2 its acceleration times time squared. And so this gives us velocity as a function of time and position as a function of time. Now, let's say you want to get velocity as a function of position. Logically, I should be able to solve one for time and plug into the other equation. So I'm going to do that. I'm going to take my left equation and solve for t. Once I take my left equation and solve for t, I'm going to shove it in for each t, which gives you this god-awful mess. I got this thing squared. I'll factor out the squared. Don't worry about keeping up with this. I'm just doing it so you can see it, but you don't have to pay attention. These A's cancel out. Once I cancel out the A's, I got this. I multiplied everything by 2. I said it out loud. Once I multiplied by 2, I'm going to multiply everything by A. Once I multiply everything by A, I went out of space and moved this up. I'm going to go and say these 2 terms cancel out. Once those 2 terms cancel out, I'm left with this. I got a negative V naught squared and a V naught squared, so I can put those together. Then I can go and add V naught to both sides. You get this equation. This equation is velocity as a function of position. That if you ever want to know the velocity of something, it's its initial velocity squared plus 2 times the acceleration times displacement. These 3 equations are called the kinematic equations. And this is what you're going to use to solve most problems in this chapter and next one. This gives you velocity as a function of time, position as a function of time, and velocity as a function of position. Well, A is acceleration, T is time, V naught is initial velocity, V is final velocity, X is final position, X naught is initial position. Almost always, though, we can define x naught as 0. When doing height, I will not say that. When doing height, I don't always define y naught as 0. I'll explain why next class. But when you're doing left and right, you always got to pick something to make 0, make it your initial. And so x naught will almost always be 0. But the nice thing is if you have any 3 of these terms, not counting x naught, you can solve for everything else. If I tell you a, t, and v naught, you can get v and x. If I tell you a, v, and x, you can get t and v naught, and so on. These 3 equations, called the kinematic equations, is how we're going to solve these problems. Okay. Questions before I do one? With my 5 minutes left? Okay. Let's say you're traveling at 30 meters per second and a light turns red. You see the light turn red and you slam on the brakes. When you slam on the brakes, you get an acceleration of -6 meters per second squared. How long does it take you to stop, as in time? And how far do you travel before stopping? So, going to go through the steps I talked about last class, or 2 classes ago. No, last class. I'm going to draw it. This is what I got. I got a car moving. I got a car stopped. That's what I care about. Let's look at what we know. I say initially this car is moving at 30 meters per second. And then it accelerates at -6 meters per second squared. Now I said I need to have 3 things to solve it, and there's only 2. But I know something else. I ask, how long does it take to stop? Stop means not moving. Not moving means 0 velocity. So my final velocity is 0. I want to know how far I travel. That means I want to know the distance from here to here, this distance. Well, I'm just going to say then let's measure it from the initial. I'm going to make my x naught 0. And there we go. I asked for how long does it take to stop and how far do you go? Questions here? Almost out of time, but okay. Now I should check that everything's in SI units, but it is. And I got the 3 variables, not counting x naught. I got v naught, a, and v. So now I just got to find equations. So what I'm going to do is I'm going to pull up all the equations. I got these 3 equations. This is how you're always going to solve kinematics equations. Put these 3 equations in front of you and start matching. What I mean is say, okay, I know v naught. I know v naught. I know v naught. I know v naught. I know a. Well, they all have a in them also. I know v final. And I want t. And also, x naught is 0. And I look at these equations and say, so I can just mark off x naught. I do the same color. And I can say, this second equation has x. I don't know x. I can't use it. This third equation doesn't have t in it. I'm looking for t and there's no t there. I can't use it. But this top equation, oops. This top equation, I know everything but t. I know v, I know v naught, I know a. It doesn't have this x I don't know. So that's the equation I want to use. That's what I mean by playing the matching game. That one matches the terms. And so v equals v naught plus at. I want to solve for t, so I'll subtract v naught from both sides and divide by a. And I can plug in 0 minus 30 meters per second over -6 meters per second squared. It's 5 seconds. Now there's a part B, and it says, what's x? If I want to find x, I do the matching game again. I can't use the top equation because the top equation has no x. But the second equation, I know everything but x. The third equation, I know everything but x. I can use either one. I get to pick. And here's the thing. When in doubt, pick whatever's easiest. That middle equation has x equals. I don't have to rearrange shit to do it. I can just plug in. The bottom equation, I'm going to have to rearrange and solve for x. Screw that noise. I'll just take the second equation and plug in my values and get it. I mean, if you really wanted to use the third equation, you could have and gotten the same answer. Any questions though? Okay. That's the kinematic equations. These 3 equations on the right is going to be how you solve almost every single problem in Chapter 2 and Chapter 3. But I'll stop there. Well, I'll pick up Wednesday with the special case of this, aka free fall. But other than that, have a good day, and I'll see you later.